So, good evening and welcome back to this live problem solving session for the NPTEL course Geology and Soil Mechanics. So, in the last week, we started solving a few numerical problems regarding earth pressure theory. So, in this session also, we'll continue that aspect. However, apart from this topic, so we we have also learned another important aspect in soil mechanics, that is stresses in soil, and mostly we have seen the applications of Boudign's theory and Westergaard's theory to determine the stresses inside a soil mass due to application of different type of loading conditions like point load, rectangularly loaded area, circularly loaded area, and so on. Okay. So we'll also take a few problems regarding this aspect. So now let's start with today's problem solving session with this problem. Since we couldn't solve this problem in the last week, so we took this problem as a homework and we discussed a little bit about this problem, that how to solve this problem. So first we'll read the problem statement and then we'll see how we can solve this problem. Okay. Again, for your information, this problem is taken from GATE examination 2023. So in this problem, a vertical trench is excavated in clay soil deposit having a surcharge load of 30 kPa. A fluid of unit weight 12 kilonewton per meter cube is poured in the trench to prevent collapse as the excavation proceeds. Assume that the fluid is not seeping through the soil deposit. If the drained portion of the clay deposit is 20 kPa and the saturated unit weight is 18 kilonewton per meter cube, what is the maximum depth of unsupported excavation? And that we have to report in meter after rounding up to 2 decimal places. Okay, so this was the question. So we discussed that for purely cohesive soil, or in the case of cohesive frictional soil, so there is a chance of generation of tension crack in the top portion of the retained soil mass. So suppose this is the retaining wall and this is the C5 soil. Okay, so there will be some portion which will be under tension, and then the remaining portion will be under compression. Okay, suppose this is the earth pressure diagram, and obviously this is the active earth pressure diagram. Okay, so in the case of active earth pressure only, we'll get this type of distribution, this tensile pressure or negative pressure in the top region of the retained soil mass. Okay, now we also discussed why we are getting that kind of tension at the top of the soil. Okay, we will not discuss in details that portion here. So now this depth we have termed in the last class as tension crack depth. Okay, so this is the tension crack depth, and we have determined the analytical expression for this tension crack depth, how we can evaluate this tension crack depth if we know the shear strength parameters of the soil and the unit weight of the soil. That also we have done in the last class. Okay. Now, in addition to that, we have talked about that if we consider another Z0, so this is the point of inflection where the sign is basically changing from negative to positive. Now, if we consider another Z0 below this point where the sign is basically changing, so what will happen? So, in the above Z top Z0 portion, means above in the sense the portion which is above this point. Okay, so in this top region, rather we can say in the top Z0 portion, the soil is basically under negative pressure. So resultant pressure is basically negative. It's basically acting in this direction. Whereas in the bottom Z0 portion, the pressure is positive and it's in the opposite direction, opposite to that uh, pressure, which is basically, or to that resultant force which is acting in the top region, top Z0 region. Now, if you calculate this resultant portion, okay, obviously for this Z0 region only, okay, not beyond that. So suppose this is your resultant pressure PA Z0, and this will be also your PA Z0. So the magnitudes of both the resultant forces will be equal, and since they are basically acting in the opposite direction, so one will cancel out or each will be nullified. Okay, one will cancel out another. So as a whole, we can realize that up to this 2Z0 portion from the top surface of the backfill, as if there is no pressure. No pressure is, no resultant thrust is basically acting on the wall. So we concluded that we can safely carry on the excavation, vertical excavation, up to a depth of 2Z0. Okay, so this was the maximum depth of unsupported excavation. So up to this much depth, there is no requirement of lateral support. If the excavation goes beyond uh, this depth, then we have to provide some lateral confinement that you can usually see in the case of excavation for metro station buildings and so on. Okay. Now, this Z0, so this is uh, this analytical form is very familiar to us, that this is the expression for the tension crack depth, but we have to keep in mind that this expression is valid only for C5 soil when there is no surcharge. Okay, first of all, there is no surcharge, without any surcharge. Okay. Now, as you can see in this problem, there is a surcharge, and at the same time, some fluid is basically placed inside the excavation trench. Okay, so we'll see what will be the consequences of putting this kind of fluid in the excavation trench, and we are also assuming that the fluid is not seeping through the soil deposit. So first, so here we'll consider two cases. So first one is with surcharge. Okay, so for that, how the tension crack depth is basically modifying, so that we'll see. And in the second case, with surcharge plus this fluid inside the trench. Okay, so we'll first start with the first scenario. So suppose this is the trench. This is the surcharge Q, and suppose this is the maximum depth of unsupported excavation, we can denote this height or depth by HCR. Okay, this is the critical height. Now, what was the principle to determine Z0? So Z0, the principle behind the calculation of Z0 is that at a depth of Z0 from the top of the retained soil mass, the lateral pressure, active earth pressure will become 0. So that means, and as we know that this variation of the active earth pressure for a C5 soil is something like this. Okay, so this is again without considering any surcharge. So without any surcharge. Now if we consider surcharge, means case number 1, so PA will be Q plus gamma Z0. This will be the vertical overburden at a depth Z0. Sorry, first let me write this expression in terms of it will be K in terms of Z only. Okay, where Z is basically measured from the top of the retained soil mass. So Q plus gamma Z Ka minus 2C root K. Now at Z equals to Z0, your PA becomes 0. Therefore Q plus gamma Z0 K minus 2C root K equals to 0, or gamma Z0 K, this will be you can write in this fashion, that 2C K minus Q divided by, okay, so 2C K root K minus Q, and therefore Z0 will be 2C root under K minus Q by gamma. Okay, so this would be the modified expression for Z0. So as you can see, so if you compare, so it's something like this, that 2C root K by gamma K. Okay, so additionally we are getting this term minus Q, okay, due to the application of charge. So that means your Z0 is basically reducing. Okay, now we'll come to case number 2, where we are having this surcharge Q, and at the same time some fluid is there inside the trench. Okay, so suppose the unit weight is gamma. Now what will be the change in the active earth pressure? The active earth pressure, this will be the variation with Z, it will be Q plus gamma Z Ka minus 2C root K, and at the same time you are having some pressure opposite to the PAZ, na? So due to the fluid, so your active earth pressure is suppose acting in this way, So the fluid pressure is basically acting in the opposite way, in the opposite direction. So you have to basically neglect that pressure. Okay, so that will be gamma fluid into Z. So this is the modified expression. Now we will follow the same concept, that at Z equals to Z0, your PA becomes 0. So therefore, Q plus gamma Z0 KA minus QC root A minus gamma F Z0 equals to 0. So gamma Z0 KA, it should be equated to 2CK plus, okay, sorry, here we'll retain this term in the left hand side only, gamma F Z0, and in the right hand side it will be UK. I think I have done a mistake in this expression. So here Q times K will be on the right hand side. Okay. So 2C root K minus Q times K divided by gamma K. So here if we take the gamma Z0 common, it will be gamma K minus gamma A Z0 minus. Okay. So as you can see, due to the fluid, what is happening? There is a change in the denominator. Okay, so it's basically decreasing by the unit weight of the fluid. So obviously the tension pack rate will be increasing, and as a whole the maximum height of unsupported excavation will increase. Okay, so this is the beneficial effect of putting the fluid inside the trench. Now we'll calculate the numerical values. Okay, so uh, as you can see, the undrained coefficient of the clay deposit is given as 20 kPa, and the saturated unit weight is given as 18 kilonewton per meter cube, and the fluid unit is the unit weight of fluid is given as 12 kilonewton per meter cube, and surface load 30. So Q is 30 kPa, Q is 20 kPa, gamma, this is gamma of soil is 18 kilonewton per meter cube, and gamma f not required for this expression. Okay, so therefore Z0, this is 2 into, okay, and one more thing, since pi equals to 0, it's a purely cohesive soil case, so Ka will be, okay, why? Because K equals to 1 minus sin phi by 1 plus sin phi, or tan square 45 degree minus pi by 2. So if you put phi equals to 0, it will be, the K value will be 1. Okay, so 2 into 20 into 1 minus 30 into 1 divided by 18 into 1. Therefore 40 minus 30, 10 by 18, 10 by 18, it's 0.56 meter. So therefore the critical height or critical depth is 2z0, so it's 2 into 0.56, so that is 1 point. But this is not the answer to this question, because we have to consider the fluid as well. So gamma fluid is given as 12 kilonewton per meter cube. So Z0 would be 2 into 20 into 1 minus 30 into 1 divided by 18 into 1 minus 12. Okay, so that means 10 by 6. So 10 by 6 is basically 1.67 meter. So therefore HCR, so this is the HCR, one 1.67, so that means 3.34. Okay, so this is the answer to this question. And as you can see, there is a big difference between these two unsupported maximum depth of unsupported excavation. So if you don't put the liquid or fluid inside the trench, so it was 1.12 meter only. However, if you place the fluid inside the trench, it will rise or it will increase to a value 3.34 meter. Okay, almost twice. Okay, so this was problem 1, the solution for problem 1. Now we'll move on to the next problem. So if we carefully observe, then most of the problems we have solved so far, so these problems were pertaining to the aspect of active earth pressure only. Okay, we didn't solve any problem concerning to the passive case. So now this problem onwards will also deal with the passive problem as well. Okay, so since this is also a very important consideration for the design of retaining wall. Okay, so in this problem we have to determine the Rankine passive force per unit length of the wall, uh, which is shown in figure 1. So this is the figure. The water table is at the level of B, and at the same time we have to determine its line of action on the base of the wall. So that means we have to calculate the resultant force and as well as its line of application from the base of the wall. Okay, so the wall is basically retaining two layered backfill. So the first layer is purely cohesionless. The phi value is 30 degrees, C value is 0, and gamma value is 16 kilonewton per meter cube, and it's having a thickness of 2 meter. Whereas the bottom layer is cohesive frictional. Angle of internal friction is 24 degree. The cohesion is 10 kPa, and the unit weight is 19 kilonewton per meter cube, and having a thickness of 2 meter. Okay, and as mentioned in the problem, that there is a water table at this level, at level. Okay, so first we'll see the generalized expression for variation of passive earth pressure with depth. Okay, so if Z is measured from the top of the backfill, so this will be gamma Z Kp plus Kp. So how this expression is coming? So if we explain a little bit about this, so we know the relationship between sigma 1 and sigma 3 on the verge of collapse or at the limiting equilibrium condition. So sigma 1 we know it's sigma 3 tan square 45 degree plus 5 by 2 plus 2c tan 45 degree plus 5. Okay, you already derived this equation in the previous chapter. Okay, shear strength of soil. Now for passive earth pressure problem, you should know that passive earth pressure, the major principal stress is the lateral earth pressure, and the minor principal stress, this is the overburden, that is gamma z. Why? Because the phenomenon which is involved in the passive earth pressure is something like this, that you are basically, for the passive case, to attain the passive state, you have to basically move the retaining wall inside the or towards the backfill. So suppose initially this is the more stress circle pertaining to the earth pressure at rest condition. So this is your sigma H and this is your sigma B. Or suppose this is the consideration where this is the sigma 1 and this is sigma 3. Now what is happening? Your vertical stress at a level, at any level, that is basically remaining constant, and the lateral stress is basically goes on increasing due to the movement of the retaining wall towards the backfill. So this sigma 3 value, which is nothing but this gamma z, that will remain constant, and the more circle will basically expand in this fashion. Now at a stage it will basically touch the more Coulomb yield envelope. This is the more Coulomb yield envelope, and no state of stress will basically can lie in this region, because this is not a feasible region. So this yield envelope, touching the yield envelope, means indicates that it is on the verge of collapse. So for this state of stress, means this is the sigma 3 and here we will get one sigma 1. This is basically denoted by the passive earth pressure. So this is the passive earth pressure. Okay, now it will basically depend on the overburden, because as you are going below, means in a deeper depth, so you will be having more overburden. So as a result, you will be having increased resultant passive earth pressure. Resultant in the sense you have to then take the area of the distribution, then only you can get the resultant passive force. Okay, so then if you substitute this sigma 1 and sigma 3, so this will be your ppz, sigma 3 is gamma z, and this tan square 45 degree plus 5 by 2, you can write it as kp. So then it will be okay, where kp is nothing but the earth pressure coefficient at the passive condition. Okay, so this is earth pressure coefficient in the passive condition. Now since the passive earth pressure coefficient is basically a function of pi, okay, angle of internal friction, so if the pi value varies from layer to layer or for a layered backfill, so it will be also varying, so it will not remain constant. And as you can see from this problem also, that pi is basically varying from 30 degree from the top, for the top layer, to 24 degree for the bottom layer. So that means there will be two kp values. Okay, so we'll first calculate these two kp values for layer 1 and layer 2. So kp1, so it will be 1 plus, or we can write in this fashion, tan square 45 plus 30 by 2, so it's 3, and then kp2 So this is layer 1 and KP2 square 35 plus 24 by 2. So it's 2.37. Okay. Yeah. Now we'll calculate the distribution of passive earth pressure. So we'll start from at z equals to 0. So Kp will be gamma z Kp. So z is 0 means the first term will be vanished. So this term will be 0. So leaving behind only 2c root Kp. So it will be 2c1 root Kp1. Okay, since we are in the top layer. So 2 into, what is the value of C? So it's again 0. Okay, so that means this Pp will be completely 0. Now we'll come to Z equals to 2 meter. What will be Pp? So Pp will be gamma 1 Z1, gamma 1 Z, or rather we can write gamma 1 H1 Kp1 plus 2C1 root under Kp1. What is the H1? H1 is nothing but the thickness of first layer or top layer. So this is your H1 and this is your H2. Both are 2 meters. Okay. So gamma 1, that is the unit weight of top layer. So that is 16 multiplied by 2 multiplied by 3 plus 2 into C1 is basically 0. So this term will not be there. So 96. Okay. Now at the interface, means at level B, we are basically having the interface between layer 1 and layer 2. So this value we have got, this one is for layer 1. Okay, so similarly we have to calculate the Pp value for layer 2 as well, since the passive earth pressure coefficient is basically changing at this interface from the value of layer 1 to that value of layer 2. Okay, so it's changing from 3 to 2.37. So therefore at the same interface we will be having two passive earth pressure. One is from layer 1 and the second one is from layer 2. However, the vertical overburden will remain same. Okay, and that is gamma 1 H1 into gamma into H1. Okay, so Kp2 plus 2C2 root under Kp2. Now it will be 16 into 2 into 2.37. Now what is the value of C2? The C2 value is 10. 2 into 10 into root under. It will be I think 106.63. Okay, so let me take this value. 1.106.6. Now at the base of the wall, that is at Z equals to 3 meter, what will be the value of Pp? It will be, the total overburden will be gamma 1 H1 plus gamma 2H2, okay, into Kp2 plus 2C2 root under Kp2. So from the top layer we will be having gamma on H1, this will be the overburden, and from the bottom layer it will be gamma 2 into H2, okay. And one more thing that you have to keep in mind, that when you will be calculating the overburden for the bottom layer, you cannot use the total unit weight. Why? Because this layer is under the or beneath the water table. So you have to basically take the submerged unit weight only. So that means gamma 2 prime. For the top layer, submerged and the saturated or total both are same, because it's under dry condition, so it will not basically create any problem. However, once you come to the second layer, so you'll have to be very careful about the unit weight when or while you are calculating the overburden pressure at level C. Okay, so that's why we have basically taken gamma 2 prime. And what is the value of gamma 2 prime? So gamma 2 prime, this is 19 minus 10. So 19 we are taking as saturated, 10 this is the unit weight of water, that means 9 kilonewton. Okay, yeah. So what do you think? This is the complete expression for PP at a depth of this will be 4 meter, not 3 meter. Okay, so 2 plus 2, that means 4. So this is the complete expression for PP at Z equals to 4 meter. No, this is not the complete expression, because you have to add the pressure component due to the water also, because we are having this water table at level B. So additional pressure from the water you have to basically take into consideration. That means this will be gamma 2, sorry, not gamma 2, gamma W into H2. Okay, now this will complete the entire expression. So gamma 1 is 16, H1 2, gamma 2 prime is 9, H2 2, Kp2 is 2.37 plus 2 into 10 into Kp2 is 2.37 plus 10 into, okay. So we'll calculate part by part. So first, the first two components, 16 into 2 plus 9 into 2 into 2.37 plus 20 into root under 2.37. So it's 149.3 plus 20, that means 169.3 per meter square. So why we have written in this fashion, that we'll see in the next slide. Okay, so we have basically separated the water contribution part and the soil contribution part. Okay, so now we'll draw the passive earth pressure distribution diagram. So this is the retaining wall, this is 0, this is 2 meter, and this 4 meter. So the distribution starts from a value of 0, then it reaches a value of 96 kPa at the interface berth in layer 1. Now at the same interface we will start from 106.6 for layer 2, that means, sorry, this is 106, this is your 106.6, and that will end to a value of 149.3. 59.3, and additionally you consider the water part. So it will start from 0 at the interface and it will end to a value of 20. Okay, so this is the passive earth pressure distribution. Distribution diagram in it. Okay, now what we'll do, we'll basically calculate the resultant passive thrust and its line of application. So for that, we'll basically split this diagram into a regular geometry. So the suppose your triangle 1, this is the trapezium 2, and this is 2. So you can split this trapezium also in two parts. So one part is rectangle and another one is triangle. However, that will basically need unnecessarily more time. So if we know the area of a trapezium and its CG, so it will be more easy for us to split the distribution in this fashion. Okay, so triangle, trapezium, and this is another triangle. So if you don't know the area of this trapezium, or you cannot recall at that moment, then you can split the lower trapezium into two parts. One is rectangle and another one is triangle. Okay, so now we'll calculate the area. So this is the serial number, means component. This is the area, and this is the CG from base. Okay, so this will be kilonewton per meter, or rather we can write in this fashion, PPI, and this is the ZI bar in meter. Okay, so for example, this is your PP1, and this is your Z1. Okay, so in this fashion we can calculate PP2 and Z2 bar, PP3 and Z2 bar, that we'll see. So this is your first passive force component, the resultant passive force component, which is a triangle. So its area will be half into 2 into 96. Okay, so that means it's 96. Now coming to the second component, so it's basically okay. So simultaneously we'll calculate the ZI bar also. So it will be your 2 plus 2 by 3. That means 6 plus 2, 8 by 3. 2.8. Okay. So from the base, so this is your 2/3. So the height of the triangle is 2. So that means from the base the CG will be h/3 plus this additional 2, since you are calculating from the base of the wall. Okay, so this is the lever arm of this passive thrust component. Okay, now coming to the second component, which is basically 106, and this is the second component, and that is the trapezium. So its two sides are 106.6 and 149.3, and the height is 4 minus 2, that is 2. So that means it will be h/2, that means 2/2 plus summation of the two sides. Okay, so 106.16 plus 149.6. So it's 255.9. And what's about the CG? So the CG, it will be basically at a distance of a plus 2b plus a plus b into h/3. So suppose this is your side A, this is your side B, and this is H. Okay, so this is the formula for calculating the CG for a trapezium. So your A is 149.3 plus 2 into 106.6 divided by 149.3 plus 106.6 into 1. So please calculate this one. Well, we are calculating the third component, so it will be half into 2, 20, and its CG will be 2/3, that's 0.67. Okay, now coming to the resultant thrust EP, so this will be summation of PCI 1 to 3. That means 96 plus 255.9 plus 20. It's 371.9, this much kilometer. Okay, so this is the resultant passive thrust. Now coming to the its line of action. So what we have to take? We have to basically take the moment above the base of the wall. So this is the resultant thrust. Suppose this is acting at a distance p bar, and this is the moment of individual passive thrust component. We have to equate this. Therefore Z bar will be summation of I equals to 1 to 3 I Z bar. If you calculate this equation, obviously after substituting the respective values, you will get the line of action of PP from the base of the wall. Okay, so for this problem I am not calculating this part, So I'm leaving up to you. So just you have to basically take the product of these individual components. So for example, 96 multiplied by 2.67 plus 255.9 multiplied by this one. So you have to calculate this value. Okay. Then 20 multiplied by 0.67. This will be in the numerator divided by this PP 371.9. Then you will get the line of action of PP from the base of the wall. Okay. So I am leaving this portion as a homework. Okay. So please solve this part. Okay. Now we'll, if it is fine, we'll move on to the next problem. And this is again regarding the passive earth pressure computation. So a rigid retaining wall is subjected to passive earth pressure. Determine the resultant passive thrust on the wall by Rankine theory. Here the height of the wall is 8 meters. Depth of water table from the ground surface is 3 meters. Cohesion is 20 kPa. Angle of internal friction is 20 degree. Saturated unit weight is 19 kg per meter cube. And the backfill carries a uniform surface of 30 kPa. Assume the soil above the water table is saturated. Okay. So unlike the previous problem, two major differences in this problem are, first of all, here is an externally applied surcharge Q of magnitude 30 kPa. Okay. And the retaining wall is basically retaining a single layered backfill. Okay. So C value is 20 kPa. Okay. C value is 20 kPa. Phi value is 20 degree. And gamma saturated is 90 kPa per meter cube. And inside the backfill at a depth of 3 meters, there is a water table. Okay. So it's not that complicated. So first we'll calculate the Kp value. Okay. So first let me write down the variation of Qpz, where Z is measured from the top surface. It will be U plus gamma Z Qp. And again, you have to be careful about this gamma. If you are below the water table case, then you have to consider the submerged unit weight of the soil, and additionally you have to consider the contribution from the water pressure. Okay, so that I am not writing in this expression. Now Kp for this soil will be 45 plus 2.04. Okay. Now we'll calculate the Pp values at different elevation. That z equals to 0. Pp, first component will be 0. Second component will be 2 into 20 into 2.04. 2 into 20 return that 2.04. Okay. In addition to that, there will be the Q component also. We have Q into 2.04. This would be 118.3. Okay. Now coming to the water level, that is 3 meter, it will be 30 plus gamma z. Now this gamma will take the saturated, okay, as it is mentioned in the problem statement, that assume the soil above the water table is saturated. So 19 multiplied by 3 multiplied by 2.04 plus okay. So 234.6 kilonewton per meter. Now we'll calculate the PP value at the base of the wall, that is 8 meters. So PP will be 30 plus. Now we have to calculate the overburden in a part by part fashion. So for the soil mass above water table, it will be 19 multiplied by 3, and below water table it will be 9 multiplied by 5. Okay. So multiplied by 2.04 plus into 20 into 0.04 plus the water part, that is 10 multiplied by 5. So this dimension is here 5 meter, 8 minus 3. So here also we'll calculate in a part by part fashion. So first two components, 30 plus 19 into 3 plus 9 into 5 into 2.04 plus so it's 326.4 plus 50, that means 376.4. That's good. Okay. So now we can draw the distribution. So if we draw the distribution, this is 0, this is 3 meter, and this 8 meter. So at the top, it's having a value 118.3, 118.3, then at 3 meter, it's 234.6, and at the bottom it's 326.4, okay. So this is 326.4 plus this water part, that is 50. Okay. So now you have to just calculate the area of this individual components. So this is your component 1, component 2, and this is okay. This is the not active. This is the passive earth pressure distribution diagram. Okay. So we can calculate the resultant passage thrust. So for the trapezium 1, it's 3 by 2 multiplied by 118.3 plus 234.6. Then for the lower trapezium, it's 5 by 2 because the height is 5 and the two sides are 234.6 plus 326.4 plus the triangle half into 50. Okay, so it will be 529.4 plus 1402.5 plus 125. It's 2056.9. Okay, so this is the answer. And for this question, we don't need to calculate uh, the line of action of the resultant passive thrust because it's not needed or it's not asked in the problem statement. So we can skip that part. Okay. So though if it is required, then it becomes very easy to calculate. You have to basically consider the individual or calculate in the individual lever arm also, and then you have to take the product, then sum it up and divide it by this. Okay, result. So this is all for problem 3. Now we'll take a few problems regarding stresses in soil. Okay, so the first question is taken from GATE examination 2022. In this problem, a concentrically loaded isolated square footing of size 2 meter by 2 meter carries a concentrated vertical load of 1000 kN. Now, considering Boussinesq theory of stress distribution, the maximum depth of the pressure valve corresponding to 10% of the vertical load intensity will be. So you have to basically determine the maximum depth of a pressure valve which corresponds to 10% of the vertical load intensity, and the distribution of the vertical stress may be given. I hope this was not given in the problem, but it's easy to recall, or you can, the derivation is not, I think, within the scope of the study, so you can recall. So this is the variation of vertical stress with this horizontal distance and the vertical distance R and Z. Okay, now first we have to discuss about what is pressure valve. So if we consider this is the ground surface and this is the square footing or any footing. For example, for this problem, this is an isolated square footing of size 2 meter by 2 meter. Okay, and this is loaded with a point load at the center. Okay, concentrated vertical load. So P equals to 1000. Now, what will happen? The soil immediately beneath this footing will be highly stressed, and as you move to a greater extent, means away from this loading zone, so your stress will be basically gradually it will diminish. Okay, so in the process of this stress distribution, the stress distribution formula you can get through this equation, that is 3p by twice pi z cube by r square plus z square whole to the power 5 by 2, where p is basically this concentrated load, vertical load. Okay, and z, this is the vertical distance at which you are basically interested to calculate the vertical stress, increase in vertical stress. Now, in the process of this stress distribution, what will happen? So you can basically draw a series of lines. Suppose this is a line. Okay. Now what will happen? What is the specialty of this line? So this line, if you draw this line by connecting a series of points which is having, each of this point is having equal vertical stress increase. Are you getting my point? So this line is basically drawn by connecting points. Each of this point is basically having equal vertical stress increase, okay, due to the application of this concentrated load. Now this line, since this line looks like something kind of a bulb, okay, so this is termed pressure bulb. Now this pressure bulb can be of different loading intensities. So as mentioned in this problem, the pressure bulb corresponding to a vertical load intensity, 10% of the vertical load intensity. Okay, so right now we are basically dealing with a pressure bulb which corresponds to a 10% of the vertical load intensity. Now the vertical extent, the maximum depth, we have to basically calculate in this curve. Okay, so this will be, and here your sigma z is basically 0.1 times. What is Q? Q is nothing but the vertical load intensity, E by A. What is P? P is the concentrated vertical load, and A is the cross-sectional area of the footing. Okay, so for this case it's 2 by 2, that means 4 meters square. So we are considering a point which is basically lies basically along the or immediately below the application of the load. Immediately below means not immediately below, so it's basically falling along the line of action of this load. So that means for this point, this R will be 0. Okay, this horizontal distance is basically 0. So this equation we can modify 3p by twice pi z cube by z to the power 5, therefore 3p by 5 z this is the modified expression for calculating the vertical stress increase at any points which are basically lying along the line of action of the load. So since R is becoming 0, so only there is a variation with Z. R is 0. So as you can see, if you increase Z, so sigma Z value will decrease. Okay. Now we have to calculate the Z value in such a way that sigma Z becomes 10% of the vertical load intensity. That means it becomes 0.1 times Q. Now what is Q? Q we can calculate in this fashion, P by A, as already we have discussed. And here the P value, okay, let as it P, so P divided by A. So now we can equate these two expression. Okay, so 3T by 2 pi Z square equals to 0.1 times Q, then 0.1. Now this P will cancel out. So 3 by 2 pi Z square is 0.1 divided by Z square is your here by 0.1. 3. A is basically 2 into 2, area of the footing, cross section area. Put under 12. So it's 4.37. So this is the maximum depth at which the maximum depth of the pressure valve at which vertical stress increase corresponds to 10% of vertical load intensity. Okay, so just you have to remember this expression, the expression for vertical stress distribution, and this one, that at what point the vertical you will be getting the maximum depth of the pressure. Okay. Yeah, so as I have discussed now, that pressure bulb is basically taking this shape. So you will be getting the maximum depth of the pressure bulb along the line of location of the P, means at the same line, this P and the point where you will be having the maximum depth of the pressure bulb, both will be along the same vertical plane. So that means R is 0. So what is R? So in Bouygues theory, suppose this is your point load. So this is your X, this is your Y, and this is your Z. Okay. So suppose you are trying to calculate at this point the sigma Z. Okay, this point A. So this is your this is your R, this is your R, this is Z. Okay, and this is capital R. Capital R means put under R square plus Z square, but you are getting this one. Now this is the distance, this is the horizontal distance from the line of application of the load, concentrated load. Now what we are getting for the maximum depth of the pressure bulb? So maximum depth of the pressure bulb it's basically occurring along the same line of action of the load. So that means this R become 0. Okay, so that's why we are basically substituting the value of R as 0 in this expression. Otherwise, you will not be having the maximum depth of the pressure valve. You will be having a depth where the sigma z value will be equal to 0.1 times Q, but that will be not the maximum depth. So at this point also, you will be having sigma z equals to 0.1 times Q. But here R is not 0. Here R is not equal to 0. But since this depth is not doesn't indicate the maximum depth of the pressure valve, so we cannot take it. So we have to take the maximum depth. Okay, so that was the question. That was the objective of this problem. So I hope it's clear. Now we'll take another problem on this topic. And again, this problem was given in GATE examination 2023. So in this problem, consider that a force P is acting on the surface of a half space. Weakness problem, as you can understand. The expression for the vertical stress at any point Rz within the half space is given as. So here in this problem, the vertical stress distribution is itself given in the problem statement. Now where R is the radial distance, there is the depth with downward direction taken as positive. Now at any given R, there is a variation of sigma z along z, and at a specific z, no, it's not last session, so we'll be having one more session on not next Sunday, coming Sunday. Okay, so that will be the last session. On 14th April, we'll be having our last session. Okay, so this is the second last session you can consider. Okay, so at a specific z, the value of sigma z will be maximum. What is the locus of that maximum z? So first we have to visualize the problem. Suppose this is the concentrated load. This is Y, this is X, this is. So it's stated in the problem that at any given R, okay, suppose we were considering this vertical plane. Now the points which are lying on this vertical plane, all points are basically associated with a constant R, okay, a given R. R is constant for this vertical plane. However, as we have seen in the earlier problem, for example, this plane, this is R equals to 0. So what's happening? With Z, your vertical stress is basically varying. So vertical stress is varying in a fashion that it's basically decreasing with increasing Z. So it's talked about in this problem statement as well, that at any given R, there is a variation of sigma z along Z, and at a specific Z, the value of sigma z will be maximum. So you will be getting something this type of distribution. Okay, so if you draw the variation for different values of Z, keeping R constant, please be careful. Keeping R constant, if you vary Z, so you will be having this kind of distribution. Now for this distribution, as you can see, this Z, for this Z, your sigma Z is. Now in this fashion, if you shift to a different vertical plane where R is having a different value, so you will be having a different distribution of sigma Z, and for a particular value of Z, you will be having the maximum sigma Z. Now what we have to do in this problem? We have to basically present, or we have to basically determine the locus of this maximum sigma z. So how this z value is basically varying with the value of r. So if we propose a relationship between r and z, so based on that equation, we can say if this is the r, so at this depth your vertical stress will be maximum. Are you getting my point? So we have to basically end up with an equation or with an expression. So based on that expression, we will be able to conclude that if this is the given r value, so at this z you will be having the maximum sigma z. Okay, so we'll see um, how we can end up with that equation or expression. So we'll start with the basic vertical stress distribution equation, that is sigma z equals to 3p by twice pi z cube by r square plus z square whole to the power 5 by 2. Now please keep in mind that we are considering r constant. So therefore, on a vertical plane, if you have to locate the point, or if you have to locate the z coordinate of that point, then you have to differentiate this distribution with respect to z to get the maximum value of sigma z. Okay, so this is from the simple mathematics. So you have to basically differentiate this equation with respect to z. So if you differentiate, first of all, this is the differentiation of u upon v. So this is u, this is v. So v multiplied v du dz, so that means dz square minus z cube square 3 by 2. Okay, v square means r square plus z square. So this you have to equate to 0. That means if you take r square plus z square whole to the power 3 by 2 as common, it will be okay. Z square also you can take it common, so this will be 3 r square plus z square minus 2z square equals to 0. Okay, that means 3r square 3z square minus 2z square equals to 0. Okay, I think I did a mistake here. So it's your u, it's v r square plus z square 5 by 2 into 3z square minus there will be one 5 by 2. Okay, 5 by 2 multiplied by r square plus z square whole to the power 3 by 2. So this 2 will cancel out. This will be 5z square 3r square 3z square 5z square equals to 0, or 2z square equals to 8. So this is the locus. This is the locus of maximum sigma z. Now if you substitute any value of r, you will be getting the value of z at which the sigma z will become maximum. Okay, so apart from the line of action of the this p value. Okay, so If you substitute any value of r, so simultaneously or subsequently you will get the value of z at which your sigma z becomes maximum. So this is the locus of maximum sigma z in terms of r. Okay. So now, so is it fine? This active earth pressure is 0 at this point, and sigma 1 is gamma z0. Suppose this is your z0. Now, if we draw the Mohr circle, with this state of stress, so how will it look like? So this is your tau axis, this is your sigma axis. So the Mohr circle will look like this. So this is your sigma 3, this is your sigma 1 equals to gamma z0. Okay, and this is the center of the Mohr circle. Gamma z0 by 2, and this is again gamma z0 by 2. Now we'll read out the options which are given to this problem. So a point circle at a distance gamma z0 from the origin towards the positive x-axis. Obviously, this is not a valid answer because we are not getting a point circle for this kind of state of stress. Okay. Then coming to option B, a circle of diameter gamma z0 passing through the origin and lying towards the positive x-axis. So it's partly correct that it's passing through the origin and it's lying towards the positive x-axis, but the diameter is not gamma z0. Yeah, the diameter is also gamma z0. Okay, so it's correct. So that means the correct option is option B. So still we'll check the other two options also. So a circle of diameter gamma z0 with its center at the origin means this type of scenario. So this is tau, this is sigma n, the diameter is gamma z0 and the center at the origin. No, this is not the case. Now option D, a circle of radius gamma z0 passing through the origin and lying towards the positive x-axis. So this is partly correct, that passing through the origin and lying towards the positive x-axis, but radius is gamma z0 by 2, not gamma z0. Okay, so obviously option B is the correct answer. Okay. Okay, so this is the answer, option. Now we'll take the last problem for this session. So in this problem, a rectangular raft of size 32 meter by 10 meter founded at a depth of 2.25 meter below the ground surface is subjected to a uniform pressure of 160 kPa. Assume the center of the area is the origin of coordinates and the corner shaft coordinates 5, 16. The vertical stress at 12, 20 at a depth of 25 meter is. Okay, so we can rather say vertical stress increase. Now we'll follow two different approaches. So first one is the equivalent point load approach. Okay, to answer this question, equivalent point load approach. Now this is y, this is x, So the center of the area is the origin of coordinates. Okay, so this is your 0, 0. This should be in scale. So this is the rectangularly loaded area. Now for the fast approach, what we'll do, we'll basically convert this rectangular load to a point load. Okay, so this is your point load P, and this P would be nothing but Q times A. So that means 160 multiplied by, what is the area? Area is 32 multiplied by 10. So this much kilonewton. Okay. Now, as per Boudigne's theory, what is the expression for vertical stress and stress? So this is 3p by 2 pi z square. Sorry, 3p by 2 pi. This is r square z square whole to the power 5 upon 2. Okay, so let me check it once. Yeah, 3p by 2 pi z cube by r square plus z square whole to the power 5 upon 2. Now what is the z value? So p already we have calculated. Now what is the z value? Z is basically 25 meter. So this is z, and we have to calculate at a point, so this is basically your z, and this is r. At this point, what is the coordinate? This is 12, 20. Okay, this is your capital R. Now z is basically 25. Now what will be the r? So r will be root under x square plus y square. That means 12 square plus 20 square. So 23.32 meter. So this is the value of r. Now if we substitute this value, 3 into 51.2 into 10 cube, 25 cube divided by 2 pi multiplied by 23.3 square plus 25 square multiplied by 2, you will get 8.2, or after 2 decimal places 8.18 This is by the equivalent point load approach. Now, and considering the thickness scale. Now, there is another approach where you can take the rectangularly loaded area and you can calculate the stresses at any one corners, any one of its corner. Okay. So, for example, at this corner, at this corner, or at this corner. So, there is a formula by which you can calculate the stresses beneath a corner of a rectangularly loaded area. So, we'll see. So, in the second approach, so stresses beneath a corner of a rectangularly loaded area can be determined as Q times this sigma. Now this Q, this is the vertical load intensity, which is 160 kPa for the present problem. I sigma, this is the stress influence factor. Okay. Now this stress influence factor you can calculate from a table, or rather we can say the stress influence factor, this is a function of two normalized dimensions m and n, where m is b upon z and n is l upon z. B is width of the rectangular area and L is length of the rectangular area, and Z is the depth where we are interested to calculate the vertical stress. Okay, so this is also a very straightforward approach. Just here you have to calculate the I sigma, but you have to be careful that the point where you are trying to calculate the vertical stress increase, that should be exactly below any means any of these four corners. Okay, not from here, not from here, not from not here, not here, or not here. Okay, so we'll visualize this. So suppose this is the rectangularly loaded area with dimension 32 meter and 10 meter. So this is your (32 meter) and this is your 10 meter. So this is width, this is length. Now we have considered the center of this rectangular area as origin. So this is 0, 0. Okay. So then this will be 5, 16 each corner. Now at what point we are trying to calculate the vertical stress? 12, 20. So this is 5, 16. Now we are interested to calculate the vertical stress increase at 12, 20. So okay, so it's basically I think the orientation, so XY. Okay, so let's change the orientation, because along X we have taken the width, Okay, so this is the center and this is the origin also, and this is 5, 16. So this dimension is 32 meters and this is 10 meters. Now we are interested to calculate the vertical stress increase at a point where the x value is 12 and y value is 20. So for example, if we say okay, so x is 12 and 20. Suppose this one. Now as you can see, this point doesn't lie below and at a depth of z equals to 25 meters. So doesn't lie below any of these 4 corners. Okay, so it's basically, it lies outside all the four corners. Now what we can do, we can basically extend the existing rectangularly loaded area in such a fashion that it becomes one of its corners. Okay, so we have extended the existing rectangularly loaded area. Okay, so it becomes a corner, because as per the principle it should be a corner, otherwise you cannot implement this approach. Now we can split this extended rectangle into this fashion. Okay, into this. So we will be having as a whole 4 rectangles. Okay, so I am naming the corners in this fashion. This is A, B, C, D, E, F, G, H, I. Now what we are trying to do, we are basically calculating the sigma z value for rectangle ABCD. Now if I am not wrong, so we can calculate the sigma z value for the rectangle means, okay, sigma z rectangle A G F or A E F G. Okay, that is the largest rectangle. Okay, so that the point F becomes a corner. So this point. Now in order to do that, we have basically considered this extra area. Okay, so this was not loaded. So what we can do, we can subtract this rectangle. So in that rectangle also it becomes a corner, and then we can subtract this rectangle. So for that rectangle also F becomes a corner. So sigma z due to rectangle E F H D minus sigma z due to rectangle F G E I. Again, if you see very carefully, to do that, we have basically subtracted this rectangle twice. Okay, so therefore we have to add this one. So rectangle H, yeah. Now you can write this sigma z rectangle AEFG by this formula Q I sigma, Q times I sigma rectangle AEFG minus Q times, okay, so Q you can take it as common, so I sigma rectangle EFHD minus I sigma rectangle FGBI plus I sigma rectangle FH, yeah, okay. So Q you know 160 kPa, just you have to calculate the stress influence factor for all of these rectangles, and we have discussed earlier that this stress influence factor is a function of M and N. Okay, so two normalized variables where M is B upon Z, N is L upon Z. B is uh, width of the rectangle, rectangular loaded area, and L is the length of the rectangular loaded area. So for each of this rectangle, this B and L will be different. So accordingly, M and N will be different. So accordingly, your I sigma stress influence factor will be different. Now, once you know the stress influence factors for all these four rectangles, you can easily calculate the sigma z value at this point 12,20 for this rectangular loaded area and at a depth of z equals to 25 meter. Okay, so we'll see only one example how we can calculate the stress influence factor for rectangle AEFG. Okay, so rectangle AEFG, that means AEFG means the largest rectangle. Okay, so where the now for this rectangle, what is the length and what is the width? So the length is, so this dimension is 4, okay, and this dimension is, because this is 516, this is 1220, so 20 minus 16 4, and this is 12 minus 5, so this is, now what is the length? So length will be 32 plus 4 36, and B, this is 7, okay, so 10 plus 7, and Z is 25 meter. M will be B upon Z, 17 by 25, and N will be L upon Z by 25. So 17 by 25 okay, so yeah, so 17 upon 25, so it's 0.68, and then 36 upon 25, it's 1.44. Okay, now come to this table. So M value is 0.68, so approximately you can take it as 0.7, and this value approximately take as 1.4. Okay, 4. So this is your N 1.4, and this is your m 0.7, 0.7 and m, so this is 0.656. Okay, so in this fashion you can get the stress influence factors for all these rectangles, and once you know the stress influence factors for all these four rectangles, so you can substitute those values in this expression. You can substitute the value of this stress intensity, vertical load intensity. So using this equation you can get the value of sigma z for the rectangular loaded area at coordinate 12, 20 and at a depth of 6. And I hope you will be getting the value somehow close to this. Okay, 8.1. So I am not solving this problem anymore, so I am leaving up to you. So this is also, you can take it as a, okay. And the last homework that we'll take from this session, so this is a gate problem. So the figure shows the vertical retaining wall with backfill consisting of cohesive frictional soil and a failure plane is developed due to passive earth pressure. The forces acting on the failure wedge are P as the reaction force between the wall and the soil, R as the reaction force on the failure plane, C as the cohesive force along the failure plane, and W as the weight of the failure wedge. Assuming that there is no addition between the wall and the, okay, so there is a spelling mistake. Between the wall and the wedge, identify the most appropriate force polygon for the wedge. Okay, so this is regarding the Coulomb's passive earth pressure theory, because here we are considering the friction of the wall. Okay, so wall friction we are considering. So as you know that in Rankine's earth pressure this wall friction was not considered, so the wall was considered perfectly smooth, but this is not the case in reality. So that's why Coulomb's theory came into picture, and this theory is on the basis of non-zero wall friction. Okay, so as you can see, this is the wedge. This triangular wedge is on the verge of collapse or at the condition of limiting equilibrium. Now on this wedge, four forces are acting: P, R, C and W. What is P? P is the reaction force between the wall and the soil. So if this is the perpendicular to the wall, this is the force P between the wall and the soil, and this is acting at an angle delta to the normal of the wall. Okay, and this is basically acting above the normal at an angle delta to the normal, and this delta is nothing but the wall friction angle. This delta is nothing but the wall friction angle. So this is one force. Now coming to the second one, R as the reaction force on the failure plane. So this is the failure plane. Okay, so this is considered as planar. So this is the normal. So this is R. So this will be acting at an angle of phi to the normal and above the wall. Then the cohesive force along the failure plane. So since the wedge is basically moving upwards, okay, so this wedge movement is basically in the upward direction due to the movement of the wall towards the backfill. So this cohesive force, the mobilized cohesive force, will basically act in the downward direction. And the fourth one, that is the weight, the weight of the failure wedge. So this will act in the downward direction. So these are the four forces. Now considering the direction and magnitude of all these four forces, we can calculate the, we can basically draw a force polygon. Now we have to choose the appropriate force polygon from the given options. Okay, so as you can see, this C, this is the most appropriate answer, because in this force polygon all the forces are basically acting in the right direction as already we have drawn for this failure wedge. Okay, so W is basically acting in the downward, C is inclined downward to the normal of the at an angle phi with the normal to the failure plane. R sorry, R, this is acting upward at an angle phi to the normal to the failure plane. C is, this is along the failure plane but along the acting towards downward, and P, this is acting towards downward at an angle delta with the normal to the bulb. So in this way we can say that option C, this is the correct. Okay, so with this we are at the end of this session, and we'll again meet for the last session on 14th April at 5 p.m. So now I'll wait for a few minutes if you have any questions or if you need any further clarification, you can ask. Otherwise, I will end this session here.